continuous signals in noise. So the problem is now something like this. So once again you have two hypotheses. So you collect some data, this is your data. Data is collected over some duration t, right? So the question is, what is the, so this is signal plus noise versus noise. So both in communication and radar, etc., this model is, so is a signal present or it is just noise, right? So what is the best filter to use, etc. If you recall, we have done the discrete case of this problem. And so the discrete case was Ris are S plus Ni versus Ni, right? So you had a, then if you recall, you form the likelihood ratio test under the, so you have all the, you find the joint density function under the two hypotheses, H1 and H0. So you have, this is all the data vector under H1 and all the data vector under H0. So you take the ratio of the joint probability density function, we showed it to be, that's the likelihood function. This we compared with a threshold, right? So the question, the trouble here is, there it was, the data was all, at least the problems we considered. Of course, if the data, the samples happens to be independent, then this is easy to find out. In general, otherwise you find the joint density function. The ratio gives you the likelihood function, which is a function of the data, right? So here what do we do? So you could say we could sample, but as I told you last time, sampling is definitely going to make this data dependent. So, and so in this case, this is a known signal. This is not the case where we have a stochastic process, but whatever I'm going to say, the same idea goes for both. So this is a deterministic signal. So a deterministic signal in noise. And the noise, let's say, is N of t is white noise. It doesn't have to be, but so that RNN is something like this. So a wide and stationary white noise. So in any case, this is a piece of a stochastic process, right? Because this is a stochastic process. So last time we learned that if you want to discretize this, then you go through the series expansion of a stochastic process by solving an integral equation, right? So the integral equation will involve the autocorrelation function. So remember, this is deterministic. So in general, the noise will have its own autocorrelation function, especially if it is not white, right? So you can look at the, then you will end up, if you want to find out the basis functions for this data, then you have to solve this integral equation, right? So this gets to be a much bigger deal now, right? So you have to find these basis functions. Then if you recall, once you know these basis functions, you can correlate with the data and create the independent samples, R1, R2, etc., so that the problem begins to look like this, and then we can use this thing. So in general, that's a complicated task, except in this case, the same idea can be established very simply. So the first observation is, look at here, we went through this last time. The noise is white. So we already, if it is just, for example, if it is just a white noise here, then the eigenfunctions can be, the phis can be any set of orthonormal functions, right? And the lambda case will turn out to be zeros, okay? I'm sorry, n0, right? It will be, so this, because this will be delta of, this will be delta of T1 minus T2 multiplied by n naught. So you can see phi k will be phi k T1 will be phi k T1. All it means is that phi k's you can choose it to be any set of orthonormal functions, sine, cosine, etc. So we have freedom in choosing the orthonormal functions, and this is a deterministic signal. So one thought that comes is, why not to take this one, the first function, to be S1t itself? Remember, the reason I put the square root of E outside is, this is already a signal with the unit energy. I am starting with the case where this signal is such that integral 0 to t s squared t dt is 1. If it is not, that's the, so of course the whole input signal has energy E. That's why I'm multiplying by square root of E here, because this signal is 1. So this is a, the basis functions are of unit energy. So this is a perfectly reasonable thing to do. Yes. Remember, the logic is from here. If the noise, the only thing stochastic here is the noise. So the autocorrelation function is turning out to be this, and this, any set of basis functions are okay. So I am going to, why make my life difficult? So I'm going to take the first function to be what I see here. All right, so the next question is, what is phi 2? So all we know is that phi 2 is orthogonal to phi 1, and all the phi k's, in fact all of them are, all the phi k's are orthogonal to phi 1. That's one condition, and there should be unit energy. Again, look at, so I'm going to take an educated guess. I have only one function here, so I'm going to say choose whatever you want here, because the noise doesn't care, and I don't care either. I only care about the first one. First one need to be something related to the signal, so I can choose it to the signal itself, right? There is no S1, just the S, right? And then if you recall, the data is, R1 data will be, you correlate the R of t with phi 1 of t. So that's going to be integral 0 to t RT st dt. And all the remaining data, Rk, will be, you correlate the R of t with the phi k's, whatever they are. So let's do that. So find out R1. So look at here. So I'm going to do this for all the hypotheses. So when I correlate this, this is going to be square of s squared t. This is 1. So do you see that this will be square root of E, right? Plus here this will be n of t s of t dt. So this I'm going to call n1. So this will be just n1. This is under h1. This is under h0. Similarly, this will be what? Anybody? What will be R2 of t? Anyone? Look at here. When I take any one of these functions and correlate with this, what do you get? Because this is phi 1. So phi 1 correlated with, remember, phi 1 is orthogonal to all of them. So this is going to be simply 0 plus nk. This is going to be just nk. Now, if the noise is also, remember these, if you recall the last lecture, these functions are designed so that these random variables are uncorrelated. And if the noise happens to be Gaussian, then they are also independent. So let's just take it under the, let me bring in one more condition here. So the noise is white and stationary Gaussian. I mean, if it is Gaussian, of course it is stationary Gaussian is enough, but it is a flat white noise case. So then we know that these RKs are independent. So now from here, the So remember, we went through all this RKs, the set of this RKs has essentially the same information as this data. That was the whole point last time. So knowing, this is not by sampling, because if you sample, you will lose the information. The information under this in a mean squared sense, and this set, this is equivalent to R of t. But these samples are, if the noise is Gaussian, then they are independent, then the joint density function becomes the product of the density function. But now look here, the only R1 has different form. R1 under H1 is this. All the other RKs are exactly the same. So this you can write this as f of R1 under H1. And this is f of R1 under H0. But here onwards, this is going to be f of N2, f of N3, etc. all the way to infinity. This also f of N2, f of N3, etc. This is not a finite series. This is, but for each term you can cancel another term. And so this only comes out to be R1 under H1 over R1 under H0. So let's so this will be Gaussian because the noise is Gaussian. So this is Gaussian with the mean E and variance. So whatever is the variance of this. So let's find the variance of that. So if I call this to be sigma squared, that's the expected value of N1 squared. That's going to be expected value of what is N1? N of t multiplied by S of t dt squared, right? And anybody, what is the answer to this? So if you expand this, you will get a double integral expected value of nt1, nt2, then you have st1, st2, yes? And but expected value of this is going to be delta of t1 minus t2, right? So this is going to be integral of s squared t dt, that's going to be 1, right? 1 or n0, whatever we have. There is an, so we picked it up to be n0, so some constant n0. Whereas this will be 0 mean with the variance, same noise. So save space, let me just write it here. So this will turn out to be, so the constants cancel off, e to the power minus r1 minus square root of e, the whole squared over 2n0. So this should be compared with the threshold. So let me remember the data is in R1. So let me bring it to the other side. So I'm going to take the logarithm multiplied by 2 n naught. So I'm going to multiply by, take the logarithm, so the e goes away. Then I multiply by 2 n naught, then you have logarithm. Then what? I bring in the e to the other side, so this becomes plus. Then finally I divide this by 2 square root of e. So this becomes n naught log eta divided by square root of e plus square root of e over 2. I'm going to call this gamma. That's the threshold. This is R1, right? But look at R1. Somewhere here, this is R1. So our best receiver is already here. So this is your likelihood statistics. So again, let's say we didn't cut any corners. We went through the series expansion of the stochastic process to do this continuous time. We didn't do sampling and this and that. We found the orthonormal functions. We have freedom, so we exploited the freedom. We chose the first function to be s of t. We did the proper likelihood function with infinite number of random variables, but most of them turned out to be irrelevant except the first one. So when you simplify it, the likelihood function turned, so this is the optimum detector, which minimizes base risk, which minimizes the base risk. So it has this is a correlation, so this is a correlator, right? Why is it a correlator? Because you can implement it by, so data comes in. So after all this, remember, so this was all in theory just to make sure you do the right thing. So the best receiver to do is what you do in communication. You can see why this is the optimum now. So as the data comes in, you correlate it with s of t, integrate it over the duration of the data. And if it exceeds the threshold gamma, then you decide in favor of H1, otherwise it is in favor of H0. You can also represent this as a match filter. Let me show you this. Just this one, if I so look at the output. So the output is going to be integral, what is it, r of t minus tau multiplied by h of tau d tau, 0 to t, right? So this is going to be integral r of t minus tau, h of h is what? S, right? H of t is s of so especially now, if you look at this at t equal to t, then this becomes t. So then this whole thing becomes so at the output, whatever is the output at t is going to be 0 to t r of t minus tau s of t minus tau d tau. And if I make this a new variable t, you can see that this is back to this one. So the correlator is also, in the white noise case, the correlator is also the same as the match filter, right? Remember, this is the match filter, right? Why is this the match filter? Just 1 hour back I showed you this, right? We went through this problem. If you have a signal coming in, you flip it and shift it, that filter is the match filter. Then this can be written as, remember, you can see this. dt will become t to 0, but which is the same as 0 to t. So this you can write it as. So this is your correlator. And this is your match filter and correlator are exactly the same.
When we derived the match filter, we didn't have the Gaussian assumption.
We didn't have the Gaussian assumption. So here, here I'm saying in the Gaussian case, the correlator is the optimum. Optimum in what sense? Optimum in minimizing the Bayes risk. In the match filter case, it was a looser condition, right? Just the maximization of the, but the same filter pops up. That's all I wanted to say, right? But let me find out the PD and PF in this case. So we have the likelihood function as what? So let's see. So we have L is what? Integral 0 to t RT ST dt. So that's going to be what? RT under H1, what is it? Integral 0 to t RT square root of E ST plus NT multiplied by ST dt, right? And here it is integral 0 to t. RT is just NT ST dt. So you can see ST squared, but that's unit energy. So this is square root of E plus N1. This is just N1, right? So I had this before there. So this is the same as saying that this is Gaussian with the square root of mean E and variance N0. And this is with the 0 mean and variance N0. This is under H1, this is under H0. So let me do PD here. So PF or PD will be both. So PF is gamma to infinity f of L under H naught dl, and PD is gamma to infinity f of L under H1 dl. So the density functions are here. And so what is it? Gamma is, I'll bring up the gamma later, the exact form. So gamma to infinity 1 over square root of 2 pi n naught e raised to minus 1 squared over 2 and so on. So let me substitute L over square root of n0, L over square root of n0 as x. So then this becomes gamma over square root of n0, right? To infinity. And we can check it out. dl is square root of n0 dx, so dl goes away. This becomes just the standard normal, right? So that's the error function, right? Error function of the function complement to be evaluated as gamma over square root of n0. Remember what is error function in the standard Gaussian? If this is error function of C. that area, right? That's the error function, right? Complementary. Now let me substitute for gamma. Look at here, gamma is this, so I'm going to divide by square root of n0. So this expression, let me just leave, I'm going to just do it here. Gamma over n0. So I'm going to divide this by square root of n0. So notice this n0 will become square root of n0 and there will be an n0 here. So this will become square root of n0 and there will be a square root of n0 here, right? Because of this. So then I take this off. Now I'm going to put it here and call SNR equal to E over N naught. SNR input. So this will become now log eta over square root of SNR plus E over N naught is SNR. So this becomes SNR divided by 2. And let me so pictorially it becomes like this, right? You have this quantity here, log eta to that you add SNR, so this is your PF, because this point is log eta over square root of SNR. Then to that you are adding square root of SNR over 2. Okay. So this distance is square root of SNR over 2. Okay. So let's do this PD. So this is gamma to infinity, the same density function but with mean square root of E. So this is L minus somewhere here. Mean is square root of E. So this is square root of E the whole squared over 2n0 dl. So here you have to be a little careful. I'm going to put L minus square root of E over square root of n to be y. So dl is square root of n naught dy. So square root of or dl over square root of n naught is dy. dl over square root of n naught becomes dy, and so this becomes 1 over square root of 2 pi e to the power y squared over 2 dy, except gamma becomes, look here, when L is gamma, this becomes gamma minus E. So this becomes gamma minus E over square root of n0 to infinity. So let me compute this quantity here. Gamma minus square root of E. Gamma is here. Where was gamma? Gamma. This was gamma, right? That was gamma. So everybody, what is gamma minus E? This is gamma, right? So gamma minus E will be what? Yeah, gamma minus square root of E. That quantity minus square root of E by 2. So this is going to be n naught log gamma over square root of E minus square root of E by 2, right? Now again I'm going to divide by square root of n naught. So that's the same thing. Square root of n naught here, square root of n naught here. This becomes, this will go away, then I will bring it down here. So this expression becomes now log eta divided by SNR minus square root of SNR by 2. So the key is here. So this becomes error function complementary of log eta over SNR minus, these are standard expressions, SNR over 2. So in this picture, anybody, where is PD now? This is PF, this area is PF, so where is PD? So from this, look at here, from this point you have to subtract, you have to go the same amount this way, and then this whole area becomes, I'm going to just shade it this way, this whole area becomes PD. So you can see PD is larger than PF as it should be. So how will you make PD larger and PF smaller? Increase? Yeah, you can see here, if you increase SNR, this term becomes small. That means this line moves to the left. And more importantly, this will become large. So this quantity will go here, this quantity will go here. So PD will increase, which makes physical sense. Of course, if you pump in more energy, you can do better detection, right? So I gave you, so we have the expression for PD, we have the expression for PF, and the final observation is that if you increase, as SNR increases, we have PD increases and PF decreases. So next what I want to do is two signal case. In other words, you have two different signals for